column 27 of Neetcode 150, largest rectangle in histogram. So the inputs will be an array of integer, for example, 717224, and basically it represents the height of each rectangle. So see this as a rectangle of, we'll see the first input as the eighth of a tower. So let's say you have a tower of 7 units high. Then for the index number 1, you're going to have a tower of 1 unit high. Then for the third entries in the array, you're going to have a tower of 7 unit high, and then 2 unit high, 2 unit high, 4 unit high. And basically we have to find the maximum area that can be covered across the different towers. Okay, so for example, this here, so this here is a rectangle. It's a 2 by 2, so it has an area of 4. It is valid. This here is also a rectangle. It is a 3 by 1. It is valid, although it is not the biggest one, as we've seen an area of 4 just before. We have this that is basically a 4 by 1, so it has the same area of the previous 2 by 2. So right now our output will be 4, but let's keep going. We're just doing this by intuition and by checking every single case right now. This is another rectangle. It is a 2 by 3, so it has an area of 6, which is the biggest we've seen so far. And we can also find another area of 6 here. So it's basically another 2 by 3. So right now it seems like 6 is the biggest one, but we have to check for this one here, which is basically a 1 by 8, which has an area of 8. Okay, so it is the biggest area. So our max loop 4 will be 8, and our output will be 8. I mean, this might seem like an easy problem to solve just with your brain, but now you want to actually write an algorithm that is gonna solve this for you. So how can we do this? So let's say that we have an array, and all our towers are incrementing by 1 each time. So let's say we only have this here. Well, it can be quite easy to compute the volume, or the area, pardon me, of each, because you only have to take the length of this here, which is 3, and you can remove the index of it. So this is going to give you the length, and the height is very, very well known, so you don't have to worry about this. So for example, here we'll simply do height, which is 1 times the length of this, which is 3, minus 0. So this will not be a problem here, right? Here you have 2, and you see that you have a length of 2, right? Because the length of the entire structure minus its index is 2, times its height is 4. And right here you can see that the length, which is 3, minus its index 2, times the height 3, is 3. So you will return 3. It might get a little bit more complex when you have decreasing order, like here, because you can't simply you can't easily compute the length of each. So we're gonna have to use a different approach, and basically to do so we will use a stack. Okay, so let's just go ahead, and in our stack we're gonna add 2 values. The first one is going to be the index, and the second one is going to be the height. So let's start here and do our first entries at the index 0. um, yeah, it has a height of 1. Okay. And the only check that we want to do here is basically is the so for example, once we've done the index 0 and now that we are at index 1, the only thing that we want to check for is if the top element um, of the stack is actually bigger than the, the tower that we have. Okay, so um, you will see this case when we will be at index 3 and when we'll be at index 5, 6, and 7. But for now, let's just continue to the index 1. So we write our index 1, and we have a tower of with a height of 2 units. And once again, for the index 2, you have a height of 3 units, um, which is not smaller than the um, top element of the stack. So we're gonna write index 2 with a height of 3. Okay, and here comes the heart of the algorithm when we reach the index 3. So we will write our index 3. It has a height of 1. Um, I'm just gonna keep keep uh keep track of my index. So let's keep it here. So right now we are at index 3, right? And now we are gonna use a while loop, and we are gonna want to pop out the first element of the stack while the first element is taller than the current element's height that we are at. So see now that we've popped the index 2, which has a height of 3, and we popped it um, at the index 3, which has a height of 1. And by doing so, we pretty much we have all the values we need to compute the area of this here, right? So we can find the length horizontally by just subtracting or finding the difference between this index and this index. So you see it's 1, and we already have the height, right? So it's going to be 1 times 3, which makes an area of 3, and we are going to check if that area is greater than the current max we've seen so far. Well, of course, because this is the first area that we computed. And there's also a cool trick here that we want to do is that we want to replace the index of the index 3 or the current index 3 basically to the value of the index of the element that we just popped out. The reason is that you can see that we are able at our index 3 to keep pushing our rectangle to the left. Okay, so it means that when you have a left tower that is greater than your right tower, the left tower can count for the beginning of this rectangle. Okay, so we are gonna go over a loop again and check if the height of the element at the top of the stack is basically smaller. It is not. It is actually greater. It has a height of 2. So this is also why we want to keep track of the current index that we are at, because the index of the element at the index 3 is gonna decrease by 1. And now it's going to also decrease by 1 because we are popping out a value that has a higher height than its own. So So see, um, the tower that has a height of 2 as an index as the index 1, and we are at index 3, so we can find that the difference is 2, and this gives us the exact length of this rectangle. It's 2, and we have the height, which is also 2, so we can just multiply them and find that we have an area of 4 and compare it with our max of 4 and see that it is greater. So we are going to update our max of 4 value. And what are we doing next? Change our index to the one of the tower that we just popped out. Okay, because now see that we can create a rectangle of 1 by 3 starting from index 1. We can also start from index 0, but it is already in the stack, and we are not going to pop it out. So yeah, we are just gonna say that it starts at the index 1, and we're gonna place it in the stack. All right. Okay. So now we're gonna move to index 4. Which has a height of 4. And the element at the top of the stack is not higher than 4, so we are gonna just put our 4 here. Okay. Great. So that's it for this round. We're gonna go to the next one, to index 5. So we're gonna start writing our index, and then the height of the tower here, which is 3. And now the element at the top of the stack has a height of 4, which is greater than the height of the current element that we are at. So we're gonna find the length or the base by subtracting the index we're at and the index of the tower we just popped out, which is 5 minus 4. It is 1, and the height is 4. Okay, meaning that we just found the area here of 4, and it is not greater than the previous max of 4, so we are not going to update it. But one thing that we're going to do is that we're going to update the index of the tower 3 to 4. Because we now know that we can start our 3 or rectangle of height 3 from the index 4. All right. And the value at the top of the stack is not higher than the one that we're hiding, so we are just going to add it here. And now we are at index 6. So we're going to write our index, and it has a height of 2. And 2 is smaller than the height of the element at the top, which has a height of 3. Okay, so now we're going to find the length of the rectangle with a height of 3, which is basically the index 6 minus 4. Okay, so we're going to start here. So 6 minus 4, so this gives us the base of 2 and the height of 3. So we can compute for that an area of 6, which is greater than the max we've seen so far. So we're going to update our max so far. And we are also going to update the index of the tower 2, because we now know that we can start a rectangle with the height of 2 starting from the index 4, right? And we're going to add this to the stack. And we're going to go to the index 7. We're going to go to index 7. with a height of 1, and the top element has a height which is taller than the height of 1. So now we can find using the the index 7, we can find that the, the rectangle with a height of 2 is going to have a length of 3. So we can find an area of 6, which is not greater than the max we've seen so far. So we're not going to update the max we've seen so far. But once again, one thing we're going to do, we are going to update the index of the rectangle with a height of 1 to the index 4. And now we're pretty much on the second part of the algorithm, where we actually have to track back our the other rectangles that we can do, because what we did is that we computed basically all the areas going backwards, so like this one. We calculated this one as well, but we never calculated the area going forward. So how can we calculate that? Well, we know that we have a length of if this is an array, because this itself is actually going to be an array of integers, where the first index has a value of 1, the second has a value of 2, right? So we know that our array has a length of 8. We know that we have a height of 1 that has never been popped out, so it has continued through the entire entire array, and it started at index 0. So what we are going to do is that we're going to take the length 8 minus the index it starts at, so 8 minus 0, 8. So we know that we can have a rectangle of 1 by 8. Okay, and we know that this is 8, and we check that with the max we've seen so far, and it is greater, so we have a max of 8. And you get the principle of the problem. Now we are ready to jump into the code. So the first thing we're gonna create is basically max so far, which initially starts at 0. And also we are gonna create our stack. And after this, we want to get the values of the height and also the indexes. So we're gonna say for I, h, and enumerate heights. Okay, this is how we do it. We want to keep track of the initial index that we are at, and also create another one that will that will be the start of the rectangle. So we're gonna say g equals I. So we don't so we keep a value I at every moment. And basically, we're gonna want to create a while loop while there is something in the stack, and while the top value has a height taller than the one we are at. So while there is a stack, and stack -1 to reach the top element. And also in our stack, we store the values index and height. So we actually have to go reach the index 1 within each value we stored. So if this is greater than height, okay, so what do we do in this case? If you remember here, you will take the current index, and we will, well, first we will pop it out. So we will pop the top element, and we will find the length, and we will find the area this way. So we're gonna say stack.pop, but we also want to keep the index. So we're gonna keep the index and the height. All right, and the reason is that we can then calculate the the well, the max seen so far. So max so far is basically going to be equal to the max between the previous max so far, and basically the height. So the height of the value we just popped out times the length, which is going to be equal to I minus end, right? And this is where we want to make sure that for example here the entry 4 uh, the entry 1 here, which initially had an index at the index 7, well, it got into the stack with the index 4 because it can start from index 4. So every time that we're gonna backtracking, we want to create another index which is equal to the index of the value we just popped out. And after this, we're gonna basically append to the stack our new index and the height. Okay. All right. So now we have the backtracking strategy on the roll. We are gonna be willing to now find the other areas going forward. So we're gonna say for I h in stack, and this is where we are gonna find our length of 8 in this problem. This is where we are gonna take that first value, and we're gonna take the length of the array. We're gonna see that the length of the rectangle with the height of 1 starting here as a length of 8. So we are gonna find the max area this way. So we're gonna say max so far equal to basically the maximum value between the max so far between the max so far, yeah, and also the height times the height times the length of the height. Okay, and this is going to be minus the index. So this way we find the length. And after this, we are ready to return the max so far at the end. It's just going to be the maximum for the entire problems. So if everything is right, it should work. And we have an error here. Okay, it was an indenting error. We have another error. Length of ice. Oh, yes, of course. All right. We have a third error. Okay. So our output was 20 and they were expecting 8. So let's just go again across the problem, see what went wrong. So we create our max so far. We create our stack. This is not a problem. And now we enumerate through 8. And we make sure that we create a second value for to keep track of the index. Then we set the index and the height to the value that we were going to pop in from the stack. And we're going to set the max so far between the max of the previous max so far and the height times basically the length, right? And then we set the new g value to the previous index, and we are appending to the stack the new index g and h. And now after this, for every index and height in the stack, we are seeing our max so far um, to be, oh, okay. I see. Yeah, I wrote a 1 instead of a I. I apologize for this. Okay, so we now solve the problem. So this is problem 27 of Leetcode. It is a hard one. It is the largest rectangle in histogram. I hope you learned from this video, and I hope to see you in the next one.